Hi, everyone. Thanks so much to the organizers for the opportunity to speak. And also for everyone here being here. It's such a wonderful group of people. I met really amazing people. Okay, so I'm Nate, and I'm talking about a multigraded version of Stillman's conjecture. And this is joint work with John Cobb, who's moving to Auburn this year, and John Sproul, who's at UW-Madison, or as I like to call them, the Johns. Okay. So let's start with the Hilbert-Syzygy theorem, which I think has been in 3 talks already, but I'll do it anyway. Okay, we're going to fix the field K for the rest of the talk. And so in 1890, Hilbert proved the following completely brilliant theorem, that if I have a finitely generated module over a polynomial ring in n variables, then it has a finite free resolution of length less than or equal to n. So here, this n is the number of variables. And so in particular, this means that the projective dimension of any finitely generated module over this ring is less than or equal to n. Okay, but maybe you're interested in bounds that don't depend on the number of variables. And this is what Stillman's conjecture says. So in 2000, Mike Stillman conjectured that, okay, if I have d1 through dm, so they were going to think about these as degrees of polynomials. So fix d1 through dm, then there exists a bound n such that any ideal in the polynomial ring generated by elements of, elements f1 through fm of degrees d1 through dm has projective dimension less than or equal to n. So this bound, so the most important thing about this is it does not depend on the number of variables. It only depends on the degrees and the number of generators. Cool. So Caviglia proved that you can replace projective dimension in this theorem with regularity. And that was the thing Juliet talked about like the height of the minimal free resolution. And that's unpublished work. Okay, it was conjectured in 2000, and it was proved in 2016 by Ananyan and Hochster in a totally brilliant paper that is incredibly difficult. I've tried to read this many times, and it's just hard. There's sort of a multi-level induction in here, and I kind of couldn't make heads or tails of it. But in 2019, Ehrman, Sam, and Snowden came and gave 2 new proofs of this conjecture, which was then a theorem. So the first proof used the inverse limit ring, and this was kind of a repackaging of Ananyan and Hochster's original proof. They repackaged it. They made it a little bit easier to read, using some sort of infinite dimensional commutative algebra techniques. But their second proof used ultra products, which is a completely different flavor, and that's what we're going to be talking about today. We're going to talk about using ultra products. Also in 2019, there was a 4th proof by Dreisma, Lazon, and Lakin, which used generic initial ideals. Also a very cool paper, but not the topic for today. Okay, so I'm interested in a multigraded version of this theorem. Why? Because of toric geometry. So as we've seen, toric geometry, people care a lot about multigraded things. Things are, the Cox ring is graded by the Picard group, which is, not Z sometimes. And so we were interested in, like, when does Stillman's conjecture hold if I take my polynomial ring, but I give it a grading that's not just like a Z grading? So the answer is not always, which is exactly the answer we were hoping for, right? It's something slightly more interesting than just saying, hey, it works for any grading. So here's a cool example of when it does not work. Oh, right, and actually, let me go back one slide and mention that I said that, right, this bound is independent of the number of variables in the polynomial ring. And so in fact, this is kind of a statement about like families of polynomial rings, right? I can take the number of variables to infinity, and that's I have like a bunch of different polynomial rings and ideals in those polynomial rings. And so that's going to be kind of a common theme, common way of thinking about this for the rest of the talk. Okay, so I'm going to define a family of polynomial rings. And the polynomial rings, let's see if the laser pointer works. Yes. Okay. The polynomial rings are these in n plus 2 variables. They got x, y, and z1 through zn. Canadian z. Not to toot my own horn, but I practiced that. Anyway, okay, so polynomial ring in n plus 2 variables, and we're going to give it a Q grading. Okay, so where we set the degrees of all the variables to 1 over n. Okay, so now I have this ideal, in, and it's generated by three things: x to the n, y to the n, and then this also standard degree n thing, sum of things. But in the new Q grading, all of these have degree 1. So I have a family of ideals generated by 3 elements of degree 1. And Jason McCullough proved that this projective dimension of this ideal is n plus 2. And importantly, this depends on n, right? So if I take the number of variables to infinity, this projective dimension blows up, even though, right, it's generated by 3 elements of degree 1 every time. And so this means that you can't have a Stillman bound on this family of polynomial rings, you know, this sequence of ideals sort of exhibits that. So this is John Cobb, one of the Johns, likes to call this a designer ideal. This is some cool ideal that Jason McCullough cooked up, maybe using Macaulay 2 or something. Okay, so let's just talk. That was a Q grading, right? So let me talk maybe a little bit more precisely about what I mean by multigrading. So things are going to be graded by just arbitrary abelian groups here. So gamma is going to be our abelian group. And then a gamma grading of a polynomial ring in potentially infinitely many variables, doesn't matter, is just a direct sum decomposition into k subspaces, where k is my field, such that if I take the gth graded piece and the hth graded piece, it's contained in the g plus hth graded piece. And this plus sign there, that's why we wanted it to be a abelian group, right? That's why we wanted it to be the indices to be a abelian group, so we can add them together. So we're going to assume that all of our gradings are connected, which means the 0th graded piece is just the field. In fact, if you don't do this, you can also come up with a counterexample to Stillman's conjecture using the same exact ideal, Jason McCullough's. Right, and then the grading support. So whenever I have a graded polynomial ring, the grading support is just the set of elements of G of the grading group where the gth graded piece is not equal to 0. And then, you know, if I have an element of such a graded piece, it's called homogeneous of degree G, and that's how we denote that. Okay, so let's relate this to what we normally think of as a graded ring. So in the standard case, my abelian group is just going to be Z, and my polynomial ring is going to be given the grading by I set all the variables to degree 1, and that's the standard grading. And just to, you know, as a sanity check, the grading support here is now the non-negative integers. Right, I've got stuff in degree 0, that's the field, and then I have the variables in degree 1, and then I have monomials in higher degree. Okay, great. So, okay, so I want a way of sort of talking about a Stillman bound explicitly. So if I take a family of gamma-graded polynomial rings, so now this is just, it doesn't even have to be countable, but I guess I've denoted it that way. So a family of gamma-graded polynomial rings, this is just going to be, I have a bunch of polynomial rings all graded by the same group, but they can have like totally different gradings, right? I don't care what the gradings are. And we say that this family has a Stillman bound if for any degree sequence in my grading group, there's a bound so on the projective dimension of any ideal in any one of the families generated by elements of degrees d1 through dm, and you know, the number of them is m. Okay, so one of our sort of 2 main theorems is that is a full classification of like which gradings support a Stillman bound. So this family has a Stillman bound exactly when the supports of all of the elements of the family are contained in a bounded factorization monoid. So bounded factorization monoid, what does this mean? So I take a submonoid of my grading group, gamma, and we say that it has, a submonoid of an abelian group, it contains 0 and it's closed under addition, but it may not have inverses. In fact, it definitely will not have inverses in this case. Okay, so it has bounded factorization if whenever I take any element of my submonoid, I can't break it apart into infinitely many, like infinitely large sums. Right, so for each G, there's some bound on the number of terms in any factorization of it. So this is like kind of hard to, you know, maybe think about on the spot, but I will give two examples, a non-example and an actual example. Okay, so first is a non-example. Let's revisit Jason's ideal. So remember, we have this polynomial ring in n plus 2 variables, and it has a Q grading. So here, the grading group is Q, right? And all the variables have degree 1 over n. And okay, so what's the submonoid generated by the supports? Well, it's just the non-negative rational numbers. And that is not contained in any bounded factorization monoid, because that thing, this, right, the non-negative rational numbers contains the number 1, but I can write 1 as a half plus a half, or I can write 1 as a third plus a third plus a third, or a fourth plus a fourth plus a fourth plus a fourth. So that means 1 has unbounded factorization, and therefore this family of polynomial rings cannot have a Stillman bound by our theorem. So that maybe our theorem explains a little bit why, like what's going on in this case. Yes. Yes, it's a great question. In fact, this example, I'll show you right here. Yeah.
One but not the other.
One but not the, yeah. So if you're finitely generated, then you have bounded factorization, but not conversely. And this one is not finitely generated. Okay, so here's maybe a slightly cooler, I don't know, a slightly cool example of, right, so I put it there. Okay, so this is, I submitted my slides last night, but then this morning I was like, I need to have a 2 pi I in my talk. So pretend this is the complex plane, and then here is 1, which you can also write as 2 pi I. So, okay, great. Anyway, so my grading group here is z squared, and so I've got right the lattice in the plane, and my polynomial rings, my family of polynomial rings is going to be Sn, which has 2n variables, and I'm going to put all of the x's with on the lattice points in the line y equals 1 to the right, and all the y's in the lattice points in the line to the left, line y equals 1 to the left. Okay, so the support of this entire family is contained in lambda, and lambda is all the points that I've sort of filled in here, right? So I've got 0, 0, it's a monoid, so it definitely should have 0, 0, but then it also has all of the lattice points on the line y equals 1 and above. And this has bounded factorization. So it's not finitely generated, but it does have bounded factorization. For example, the red point 0, 2, I can write it like in infinitely many different ways as sums of things, right? I can write like 0, 2 as like this thing plus this thing, or as, wow, this is like hard to do, this thing plus this thing, etc., right? But none of these factorization, the size of each of these factorization is like less than or equal to 2, right? So it's never going to be, I can never break it apart into like, just like we could in Q as like 1 is a half plus a half, or a third plus a third plus a third, etc.
The support is contained in something finitely generated. So is that enough, or is there some class of gammas that has this bounded factorization property, but is not even contained in a finitely generated?
Oh yeah. So wait. Are you saying? Whoops. I think I'm about to.
It's contained in z squared. Your first example Q is never going to work because you could.
Yes. I get your. Yeah. Of course. You can do this. Yeah. So I can do this with like infinitely generated abelian groups. Is that what you mean? Mm-hmm. Yeah. So I could do it with like z to the like maybe an like countable direct sum of z's. Yeah. So this actually does work. In fact, it doesn't quite matter for the theorem, but yeah. I'm saying let me go take. Yeah, so like you mean if I filled in the rational points on the line? Yeah, I think actually you could. That's a good point. But just not on the line y equals 0.
Right.
Yeah, that's a really good point. Yeah, I have not thought about that example. No. Okay, so our goal is going to be to prove one direction of this theorem. So the other, we're going to try and prove the hard direction. So the other direction is a bit easier. And you can, our paper just dropped on the archive like a week ago, so you can go check it out. It's not hard at all, but this is the harder direction. And so for technical reasons, it's going to be easier to work with an equivalent version of Stillman's conjecture, where we translate projective dimension into a statement about regular sequences and collective strength. So bear with me for a second. This is like maybe the most technical commuted algebra here. Okay, so the equivalence is that a family has a Stillman bound exactly when, for any degree sequence, there's a bound such that if I have polynomials f1 through fm in any of the families of the fixed degrees, if they have collective strength bigger than n, then they form a regular sequence. So you may be familiar with what a regular sequence is, and I was definitely not familiar with what collective strength means, so here's what it means. The technicalities won't be super important. So the strength of a polynomial is the minimal r such that I can write it in the following sum. Oh, it's so hard to do. Right, in the following sum. So as a sum of two elements, two homogeneous, sums of pairs of homogeneous polynomials, each of degree larger than 1. So just as a sanity check, variables in a polynomial ring have infinite strength, right? I cannot write a variable in this way at all. So if I have a collection f1 through fm of polynomials, their collective strength is just the minimal strength of any non-trivial homogeneous k-linear combination. And the only thing that you will need to know about any of this is that a collection of polynomials has infinite collective strength exactly when they are k-independent mod the maximal ideal squared. So here S plus is just the ideal generated by all the variables, the unique graded maximal ideal. Okay, so here's the proof. Okay, I've written the claim up above. So for any degree sequence, there's a bound such that for all families of polynomial rings with support contained in my bounded factorization monoid, and for all elements of any element of that family, member of that family, of the fixed degrees, if they have collective strength bigger than n, then they form a regular sequence. So the proof is going to be by contradiction. So I've now negated that statement, right? So the proof starts with a negation of that statement above. And so the upshot is that we get, right, so this means there exists some degree sequence such that for all n, there exist polynomials in, collection of polynomials of the given degree sequence in some member of the family, which have collective strength bigger than n, but do not form a regular sequence. And I've collected this into, I'm using the word collected a lot. I've collected this into the following diagram. So in Sn1, first member of the family, I have a collection of polynomials. They have the specified degree sequence. They have collective strength bigger than 1, but they do not form a regular sequence. And I have a second member of the family, same thing, except they now have collective strength greater than or equal to 2. And so I can sort of package this information into a collection of sequences of polynomials. So now this thing, so each of these, I'm just saying like this is just a sequence of these polynomials. And wouldn't it be nice if these sequences were actually elements of some ring in which I could discuss the collective strength, their collective strength, whether or not they formed a regular sequence? Wouldn't that be nice? And Ehrman, Sam, Snowden, this is exactly what they did. So so they were working in the standard graded case, and they said that the limiting object should be the ultra product. Okay, so ultra products, kind of a weird construction. We're going to fix a non-principal ultra filter in the power set of the natural numbers. So here, why are we doing the natural numbers? It's the indexing set of our family of polynomial rings at the bottom. So what a non-principal ultra filter is doesn't really matter, but you should think about these so it's a collection of, right, so it's a subset of the power set. And so we should think about these as sort of forming neighborhoods of a fictional point in the natural numbers. It's a non-principal ultra filter, which means they're not actually going to be neighborhoods of a point, but they will, but they sort of behave like neighborhoods of some fictional point. This ultra filter is going to be used to take a quotient of the product, which is called the ultra product. So we say that a property holds almost everywhere if it holds for all members of all elements in some member of this family, of this ultra filter. And then the ultra product, you take the normal product of all these rings, and then I quotient out by the relation where two sequences are equivalent if and only if they agree almost everywhere. we're working with graded rings because, I'm going back a slide here, because each of these sequences, right, this is a sequence of elements of all of the same degree. And so we want to, in fact, work with the graded ultra product, where it's a subring of the original ultra product, which consists just of sequences where all members of the sequence have degree D almost everywhere. So that's the Dth graded, the Dth graded piece. So it turns out that by Ehrman-Sam Snowden, this is a polynomial ring. So if I take an a graded ultra product of a bunch of polynomial rings, I get another polynomial ring. But this polynomial ring is humongous. It's in a lot of variables, like uncountably many variables. Okay. So now we can fill in. Oh yeah. Do you have a question?
It's like there's no relation.
Yeah. It's weird. It's crazy. So they prove this using like derivations. They have some characterization of like when you have a graded polynomial ring in terms of derivations on the algebra. And in fact, we use, so I'll explain this in a second, but that was exactly the motivation we prove our thing using a slightly different technique, and that was exactly the motivation because this thing is technical. It's a very cool paper, highly recommended. Okay, so now we can fill in the question marks that I had in my previous little diagram. Okay, so remember we have okay, so I have my first collection, in my first polynomial ring, I have my first collection of polynomials of the specified degrees. They have collective strength greater than or equal to 1, and they do not form a regular sequence, and so on, right? I have the collective strength is increasing. None of them form a regular sequence. And it turns out that when the collective strength, so that means that these sequences are in fact elements of the graded ultra product down here. And because the collections, the sequence of collections, the collective strength goes to infinity, actually these sequences in the graded ultra product have infinite collective strength. And it turns out that when you have a collection of elements of infinite collective strength in a polynomial ring, they're part of a polynomial basis. So they're algebraically independent, and this means they're a regular sequence. So I can fill in this yes. Okay, so we're almost at a contradiction, right? Remember, we started with negating the statement, right? So we're trying to get to a contradiction here. And the contradiction is going to come from this whole sequence of no's and that one yes. But we need some way of translating between being a regular sequence in the graded ultra product and being a regular sequence in the factors, maybe almost everywhere. So Ehrman-Sam Snowden's, in the standard graded case, their solution to this is to use codimension, like the commutative algebra notion of algebraic geometry, commutative algebra notion of codimension. And it's a bit technical. Constitutes a large part of the paper. And it turns out that when you switch from the standard grading to like multigradings, this part becomes incredibly difficult. I think that I can do it, but it's very long and very annoying, and no one wants to read it. And I don't want to. No one wants to read it, including me. So, so our approach is going to be instead to use model theory. So I am not a model theorist. Our resident model theorist is John Spurl. And he's been very patient explaining model theory to me. This slide is the amount of model theory that I know. Okay, so it turns out that ultra products in fact belong not to commutative algebra originally, but to model theory and logic. And they're a beautiful tool. The fundamental theorem of ultra products is a theorem about it's Walsh's theorem. It's a theorem about first order statements. So for my purposes, a first order statement is just a statement about a polynomial ring, which only quantifies over elements and not ideals, not subrings, not anything else, right? So I can only say things like for all x in the polynomial ring. I can't say like for all ideals, something is going to happen. And Walsh's theorem, so this is pronounced Wash, maybe. Is it? Okay, I did it. Okay, great. I practiced that too. Yeah. Yeah, I said Los for a long time, and then John was like, no. Okay, so Walsh's theorem says that first order statements hold in the ultra product exactly when they hold in the factors almost everywhere. This, it seems like, let me just go back here, right, we wanted a way to translate regular sequence between the rated ultra product and the factors. And so this seems like the perfect tailor-made thing for this. But it turns out that we actually want this to be true in the graded ultra product, which is smaller than the ultra product. And so to do this, we have to switch to something called a lambda bounded statement. So up above, first order statements are statements which only quantify over elements. And now lambda bounded statements are statements which only quantify over elements of some, less than or equal to some degree. And so the second main theorem of our work is graded Wash's theorem, which says that if you have a lambda bounded statement, then it holds in the graded ultra product exactly when it holds in the factors almost everywhere. And it turns out that being a regular sequence is a lambda bounded statement. And so that's the end of the proof. Right, we have our diagram again. We have a whole sequence of no's, right? None of these is a regular, none of the collections in the sequence is a regular sequence, but the collection of sequences in the graded ultra product is a regular sequence. Being a regular sequence is a lambda bounded statement. So by graded Wash's theorem, right, so they are a regular sequence, right? This is a yes. This forms a regular sequence. Being a regular sequence is a lambda bounded statement. So by graded Wash, it must hold in the factors almost everywhere. But in fact, these are all no's, right? And I didn't tell you what an ultrafilter was, but ultrafilters never contain the empty set. So contradiction, and that's the end of the proof. Cool. Thanks so much.